Beijing, the capital of People's Republic of China, one of the largest cities in the world, a place where tradition meets modern-day culture. This complex and beautiful environment was the setting for our project. In the northern part of the city lies the Huanan Road district, mainly residential but also containing a large number of commercial buildings along the main streets and avenues, on one of which we have chosen a site for our building. The site is located on Jianan Road, one of the large ring roads that surround Beijing, which is a high-frequency location. This is a suitable location for a municipal government building. Just north of the site lies the Olympic Village, constructed during the 2008 Summer Olympics. This means that the site is accessible and easy to navigate to. Accessibility is defined by the number of subway stations and bus lines surrounding the site. Also, the main roads contain cycling lanes, which contribute to the accessibility. The building design was guided by the location itself, while keeping in mind the usage of space that it provides. The main long axis runs north-south, and the short axis from the east to the west, following the orientation of the Beijing street grid. This was used to define the areas of the facade to be or not to be transparent, taking into account the benefits of the sun's energy and the beauty of daylight. The southern and part of the eastern facade are tilted towards the ground, forming a 71-degree angle with the horizontal plane. This was done to minimize the entrance of sun's rays during the summer months, but also allowing the rays to enter the building during the winter months, thus not overheating the space in the summer and heating it up during the winter. The architectural aspect of the building was simple, providing the municipal government building with all the required rooms and spaces, but also adding some features which contribute to the work environment comfort, like the skylit atrium for the office space, large glass facades for the common grounds, and a central garden designed in the traditional Chinese style which offers a place for relaxed breaks. The goal was to design a sustainable, eco-friendly, healthy and pleasant workspace, a municipal space that everybody would be glad to visit. To accomplish this goal, architecture and engineering had to work hand in hand in producing a quality system while it's not jeopardizing the aesthetic value of the building, and also the city itself. Envelope was designed to exceed standard requirements, thus increasing the building's overall performance. Window-to-wall ratio is kept up to 40% as prescribed by the standard, and no trade-offs were made regarding U values of envelope constructions. We especially focused on selection of recyclable materials. Exterior walls consist of well-insulated steel frame walls with acoustic tiles, thermal insulation, vapor and moisture barriers, and glass curtain walls. Steel frame wall, as well as raised floor for the underfloor air distribution ducts, have air barriers which increase the R value of these constructions. Thermal insulation is produced from up to 90% recyclable plastic, PE bottles, and is 100% recyclable, resistant to mold, zero ozone depleting potential, and zero global warming potential. Metal frame walls are also recyclable, relatively easy to assemble, and cheap for transport. Vegetated surfaces, skylights, and PV panels are roof-installed features which increase its R value. The climate of Beijing is clearly of the continental monsoon type. It is classified as mixed humid, with relatively cold dry winters and warm humid summers. For obtaining psychometric chart of Beijing climate, we use Climate Consultant 6.0, only for working hours, from 6 a.m. to 6 p.m. Necessary HVAC and architectural design strategies for providing maximum comfort are listed on the chart. Another interesting fact is cloud coverage. The sky is rather cloudy during the summer, occurrence not common during the winter months. This cloud coverage ratio means equivalized electricity production by PV roof-mounted panels throughout the year, making better balance in electricity power demand from the network. Two options for HVAC and auxiliary system were compared. Option 1, gas boiler for heating and air cooler chiller for cooling. Option 2, ground source heat pump covering both cooling and heating loads plus PV. Inflation rate was assumed to be 3%, and the fuel cost escalation rate was based on a 10-year average increase, as suggested by the project requirements. Period of 20 years were chosen for the analysis, representing the approximate lifetime of HVAC equipment. The results led to a conclusion that the proposed case, option 2, would make noticeable savings during a 20 years period of time, with equity payback period of 9.8 years and net present value of $316,024. With equity payback period of 9.8 years and annual life cycle savings of more than $25,359, ground source heat pump proved to be a better solution in economical terms. In addition, the proposed case will reduce greenhouse gas emission by 85.1 tons of CO2 per year, which is equivalent to 35,835 unused liters of gasoline. In addition, there are more arguments in favor of selecting ground source heat pump system, which are several ground source heat pumps with total nominal power 150 kilowatts could cover both heating and cooling peak loads and serve as a spare service water heater. If combined with PV panels of 32 kilowatts, the CO2 emission would be reduced by 45 tons of CO2 per year, giving the possibility for greenhouse gases reduction in the following years of system utilization. Conditions in most thermal zones are similar. This means that all thermal zones except the server room can be treated by the same HVAC system. Dedicated outdoor air system with heat recovery equipment is used to constantly provide 100% freshly treated outdoor air to the occupants whilst recovering sensible heat from the return air with the heat recovery wheel. Implementing large transparent surfaces to the facade, window-to-wall ratio of 40%. We minimize the need for artificial lighting. For artificial lighting, in the whole building, we used LED panels and tubes. Different types of sensors and controllers are to be installed in areas with different occupancies, in order to use minimal energy needed for the required illumination level. Lights in large spaces on the perimeter and atrium will have automatic responsive controls for side lighting and top lighting. The lights in primary and secondary daylight areas will be continuously controlled with dimmers. Relatively smaller spaces and rather discrete occupancy profiles, such as enclosed offices, restrooms, classrooms, meeting rooms, and emergency vehicle garage, will have ceiling-mounted occupancy sensor devices to shut off lighting after the space is unoccupied longer than 10 minutes. Facade lighting consists of wall-mounted LED lights of 3-watt power input. Decorative lighting consists of LED solar lanterns which recharge during the day and are completely independent from the grid. To determine building performance, 2 separate simulations were done for the selected HVAC system. Analyzing the project requirements and trying to fulfill all the comfort needs of the occupants, we decided to implement a sophisticated and elegant solution to meet the demands. We started out with a classic underfloor air distribution system. By developing the idea further, the solution was completed with the zone reheat terminals. The UFAD provides isothermal environment in the occupied zone, what is also confirmed by the air distribution efficiency equal to 1.0. Therefore, another temperature zone takes shape in the ceiling area, which is warmer. This process, known as stratification, has beneficial effects on thermal comfort of the occupants. Furthermore, because of the diffuser layout and density, there is no need for high air inlet speeds and very low inlet temperatures. The occupants could adjust the airflow to suit their individual needs by turning the bars around in the sockets, thus directing the airflow. Recent field research, ASHRAE sponsored research project 1161RP, has found that building occupants who have no individual control capabilities are twice as sensitive to change in temperature compared to occupants who do have individual thermal control. What this indicates is that people who know they have control are more tolerant of temperature variations, making it easier to satisfy their comfort preferences. Based on this, the occupants enjoy greater freedom in the selection of clothing, no fear from draft and icy airstreams in cooling mode. CO2 sensors are mounted in the space such as conference rooms or break rooms, as the standard specifies, to maintain the comfort conditions when the space occupancy rate is high. The corridor surrounding the atrium on the first floor shares the same airspace with the ground floor atrium space. Therefore, it's necessary to maintain a higher pressure in the corridor to avoid incidence of the hotter and polluted air from the upper layers of the atrium. Conducting the CFD analysis in Design Builder software for the cooling operation, we took the atrium and a common small office to show the streamlines and the temperature zones formed by the underfloor air distribution system, implemented in our building. Because of its height of 9 meters, 30 feet, the atrium is considered a large space. The air outlet diffusers are mounted into the first floor ceiling because of the atrium's interior layout. Detailed analysis in the atrium show that the calculated flow of 0.648 cubic meters per second was not sufficient to maintain the required thermal conditions in the room. A significant increase in total airflow of 180 liters per second was necessary to meet the required conditions. to ensure the right comfort conditions in the occupied zone. The most important advantage is that we don't have to cool the unoccupied zone above 1.85 meters or 6 feet. So this volume is used to collect the warmer air and all the pollutants arisen from the occupied zone, and directly extracted through the air return diffusers. Taking into account the well-known conditions of the outside air in China, even more in Beijing, we had made great efforts to supply the occupants with well-filtered, fresh air. Outdoor air monitoring equipment was mounted near the fresh air inlets in order to continuously follow the outside air quality, as the table shows. The diagram shows the concentration of PM 2.5 pollutants for every day the highest value, from 2009 to 2014. Since April 2008, there have been at least 1,812 days where air quality in Beijing had reached at least unhealthy levels. There have been only 2 days on which levels did not exceed good. Average rainfall in Beijing is 48.1 millimeters per month. Theoretically, a rainwater harvesting system installed under the approximately 1,000 square meters of vegetated roof surface could annually capture around 570 cubic meters of water. With that in mind, placing a rainwater harvesting system under vegetated surface is a good solution that could notably reduce consumption and cost of potable water for irrigation and toilet flushing. Sand, small brick, charcoal, and pebble have the ability to filter the harvested water to a certain purity. With adding advanced filters and UV purifiers, the water is used for toilet flushing. Furthermore, the precisely controlled and operated irrigation system uses the accumulated supplies from the rainwater harvesting system and greywater storage tanks, so that there is no need for potable water to irrigate the gardens. Fresh water is a treasure. This sentence was the spirit of our efforts to look around, find the best solution and implement it in our building, to save as much as possible fresh water for the next generations.